Linear programming. Linear programming is a mathematical technique. LP it is also called. LP is a mathematical technique or mathematical problem which can be which is used to optimize the resources available in any situation. This will give the best solution out of the solutions available. So the best solution, whether it may be maximizing profit or minimizing cost. This objective function has minimum constraint. It has to meet the restrictions are called constraints generally. So the solution will meet the constraint as well as the max, and it satisfies the objective function. So, few steps in linear programming is it must have objective function. A linear programming problem must have an objective function. Objective function is nothing but what is the objective of your what is the objective you are doing. It's a objective function. Second is constraint equation. Second is constraint equations. So this constraint equation, to understand it clearly in layman terms, it's called actually restrictions to the your problem. Suppose for example, if you want to maximize the profit in your business, but at the same time you have to minimize the uh, restrict the expenditure up for a particular year, some 1 million, like that. So restrict the expenditure and restrict the some other for every so many restrictions will be there, right? So all the restrictions are all called constraints. There are non-negativity constraints. These are called, suppose sales always has to be positive, there won't be negative number. So that's why we take only positive values. That's why whatever the value variable you are finding out, whether it may be number of labors required for the doing any operation, or number of warehouses are required to store a particular particular material to meet the demand. So these are all positive numbers actually. So these positive, that's why always there is a solution, we expect the solution has to be positive. That so it's called non-negative constraints, and they has to be mostly integer. That will come again, that is called integer programming. We only study linear programming which gives the results of fraction values also. So first, after getting these three, objective function, constraints, and as well as non-negative constraints, so first step is this one. Next, create the Cartesian equation into that intersect form. Create the constraints equation equations into intersect form. To draw on a graph. Actually, this linear programming problem, in a simple case, if you have only two variables, then you can solve by by drawing on a XY chart, 2D diagram. So for that purpose, you have to convert the constraints into intercept form. then you can easily point out the where they are meeting the x-axis and y-axis. Just draw touching those two lines, x-intercept and y-intercept. That is called one equation. So by drawing multiple equations, whatever the area common to the multiple all the equations is called the best solution. So in graphical method we use this. Next, after constraints, then mark the constraint space. Constraint Mark the constraint equation on a graphical solution space. Nothing but an XY chart on a graph. So once after identifying the solution space satisfied by all equations, next step is identify the solution space which satisfies all constraint equations. And non-negative constraints. Obtain the corner points of the graphical solution space. Next, the corner points of the solution space are initial basic feasible solution. Out of the corner points, one point will give the best solution, that is called optimal point. The point which maximizes or minimizes objective function. Is the optimal point, and it is the solution for the it is the best available solution for the linear programming problem. So this is simple way I can say one graphical method. So before there is another thing which we need to discuss, two points regarding graphical method. We generally always take only convex sets. What is convex sets? Or convex set or convex solution space. The solution space, if you join any 2 points, any 2 points in the solution space, then the line, entire line, has to stay in the solution space. It is called convex. For example, suppose there is a solution set with two constraint equations. So this is the area of solution set, and in this I am drawing 2 points. Wherever you can select any 2 points, but all the points, these 2 points line, the line has to, if you join the 2 points, the line has to stay in the solution space. Then it is called convex solution space. We accept only convex solution set yeah, optima that solutions only. Convex space solution. Non-convex is, suppose if you have a solution space of non-convex solution space. So opposite to the above definition. For example, if we have a solution space of just see one second. So for example, the solution space is somewhere it looks like, okay, it won't generally, this is I am just trying one rough diagram to understand. The solution space is, we got the solution space, this one, to meet all the constraints. There are 4 or 5 constraints. So if I join 2 points in the solution space, one is join 2 points, joining 2 points here and here. So this line is going outside the solution space. So this area outside. So that's why it is non-convex solution space. So we try to avoid the non-convex solution set. So in linear programming problem, first and solution is graphical method. As we have discussed graphical method, how to start the approach. So we solve few problems. Zmax equal to 4x1 plus 6x2 subject to x1 less than equal to 2, x2 less than equal to 4, x1 plus x2 greater than or equal to 3, and another constraint is x1 comma x2 greater than or equal to 0. These are non-negative constraints. So for this, start with simple graph. We know by seeing the problem itself, yeah, there are two variables. Okay, so just take the x-axis one variable x1 and y-axis one variable x2. Take first constraint x1 less than or equal to. So mark point 2. So x1, this is x1 line. It is less than or equal to 2. x1 is less than or equal to 2. So the line satisfies this total entire area below 2 x1. So x2 less than or equal to 4. Mark 4 on the graph and draw a horizontal line, and the area below this is called solution space which satisfies both two constraints. x1 plus x2 greater than or equal to 3. Then mark the intercepts 3, another one is also 3. Draw a line joining those two, and it is going out greater than or equal to 3. Earlier one are less than or equal to, that's why we have drawn towards the origin. If greater than means away from the origin. So now the solution space satisfying all these constraints is the now it gives the initial solution space. So out of these points A, B, C, D, all these points are called corner points. So these corner points will give every, so if you substitute the corner values of corner points, so suppose for example A value is 0 comma 4. Next B is how much, 2 comma 4. If you simplify those two equations, then you will get that C is nothing but 2 comma 1. D is nothing but 0 comma 3. So if you substitute these values into objective function z max equal to 4x1 plus 6x2, so then za equal to 4x1 is nothing but 0 plus 6x2 is nothing but equal to 24. Similarly zb 4x1 plus 6x2 32. zc 4x1 plus 6x2 14. zd equal to 4x1 plus 6x2 18. So out of all of these values, our objective function is maximization. What is the maximum value? 32. So optimal solution is equal to zb, which is the solution is at b, which is nothing but 2 comma 4. So x1 equal to 2 and x2 equal to 4 is the optimal solution. The optimal value is nothing but 32. So this is a simple way to solve the graphical method of linear programming problem. So here there are different types of problems in the graphical method itself. We solve one by one. Then after completion of this, then we go to simplex method. So before going to the further different time models, we will just brush up the few fundamentals. Decision variables. What are called decision variables? The decision variable means the variables whose which are required to found in the problem. The variables which are required to found which are required to found for maximization or minimization of objective function. So in this problem, for example, x1 comma x2, these are called decision variables. We are calculating the x1 and x2 value here. There are more than two variables, then we can go with another simplex method. Some other methods are there, special techniques. Next, objective function. You know that objective functions are the first equation. Constraint. Next is feasible solution. What is a feasible solution? A set of values which satisfies the constraint sets. This may be feasible solutions to the linear programming. A set of a set of values of decision variables. Set of values of decision variables, nothing but x1, x2. A set of values of decision variables which satisfies the constraints are called feasible solutions. So in the present problem, example, corner points. All corner points in graphical method or initial that feasible solution. So optimal solution. What is optimal solution? Out of the feasible solution, only one solution gives maximum or minimum value. Out of the out of the feasible solution set, feasible solutions, you may have more feasible solutions. One solution which gives extreme value, either it is negative or positive. Negative means that means lower. Extreme value or extreme value either high or low based on the objective function. So if our objective function is maximization, then the optimal solution is maximum value. If objective function is minimization, optimal solution is minimum value. Example, maximum value for maximization problem. Okay. In general, linear programming problem formulation is important. So formulation, we have already discussed a few condition. Formulation of linear programming problem. So here a linear programming must have objective function. So z is equal to I equal to 1 to n ci xi, subject to constraint sigma aij xi, where I equal to 1 to n, and then xi is greater than or equal to 0. In a simple way, these are the constraints and non-negative constraints. So the constraints aij xj less than or equal to or greater than or equal to, anything may be possible. Generally we take less than or equal to. Okay, and we have already discussed that xi is a decision variable, c is the unit contribution of the decision variable, coefficient nothing but. This coefficient can be negative and positive, but x value has to be always positive. Next, aij, a is exchange coefficient of the variable in the ith constraint. Exchange coefficient of the variable in constraint. B is constant in constraint equations. So these are the few points which we need to remember. So if we have maximization problem, if you want to convert to minimization, multiply the objective function with -1. Then it will convert into minimization problem. So maximize z equal to c ci xi is also written as, so can be written as minimize z equal to sigma minus ci xi. So just multiply the objective function with minus sign, and always constraints has to be less than or equal to or greater than or equal to. Always constraints has to be less than or equal to, less than or equal to, that means, so either less than or equal to or greater than or equal to sign. If any equality sign, the equality sign constraints has to be converted into two constraints. Two constraints. One is less than or equal to, another one is greater than or equal to. then you can replace the equality constraints with the same constraint written twice. One is less than or equal to, another one is greater than or equal to. So this is the way initial steps you need to take care for any simple linear programming problem. After creating the linear programming problem, then you can take the select method for solution solving. If it has only two variables, then you can go ahead with graphical method. More than two variables, then you have to go with simplex method. So next, another type of problem, different case, z max equal to 3x minus y, subject to x minus y less than or equal to 10, x less than or equal to 20, where x comma y greater than or equal to 0. This is our problem. For this solution, how we start is same. X, Y, Y, draw the on XY axis and mark the points. The first convert into a intercept form. Y by minus 10 less than or equal to 1. X by 20 less than or equal to 1. These are the equations. So intercepts has to be multiples of 10. So with that help, first we can draw intercept y negative, so minus 10. Any other numbers, that's it. So x y 10. So first draw a intercept which is passing through x 10 positive value and y minus 10. So this is the intercept. So it is less than or equal to sign. Less than means towards origin. From that point to, this is a constraint 1, this is 2, 1 1. The arrow mark showing towards that entire region is a satisfying the solution. So next, another, by adding another constraint x is equal to x less than 20, there is another constraint you can add this way. So this is called 2 constraint 2. So the region less than, this is also less than or equal to, less than means towards the origin, the solution. So the common region now which satisfies both constraints is the region which is satisfying constraint as well as a non-negativity constraint. We have to take only positive value. So this is a region which satisfies both. So the region extends. It extends towards the end, infinity. So that's why it is this solution has unbounded solution space. It's a case of unbounded. The objective function is maximization. Why unbounded, I will say you. For example, I have taken this point 1. Suppose for example it is A, it is B, it is C, and another side we unbound, it is boundary is unlimited. A is 0 comma 0, B is 10 comma 0, C is 20 comma 10. So these are the equations we have. Substitute in ZA, ZB, ZC. ZA equal to, ZA is nothing but equal to 0 comma 0, 3 into 0 minus 0 is nothing but 0. So ZB is equal to 3 into 10 minus 0, 30. ZC 3 into 20 minus 10 is equal to 50. So here what we understand is, if you look at the ZC is the highest value. As of the three values we have, objective function is satisfying maximum optimal solution as present, it is C 50. So if you look at the line which satisfies, if you go towards the end like infinity, y value increases. So y value increases, your objective function decreases. So optimal solution is 20 comma 10. Optimal value is, optimum value is 50. So this is even though the solution space is, generally the solution space has to be, have boundaries, have closed by boundaries, but here on three sides it is closed, one side it is not closed. So that's why it is called unbounded solution space. So it has optimal solution but unbounded solution space. Suppose if the objective function, if I change the objective function to minimization 3x minus y, what is the best answer? Then the solution, as we got ZC, if you look at ZC 3x minus y, right? So the y value goes on increasing because it is infinity, right? Suppose if the y value keep it as 10,000, 3x is always fixed 20 max, or you can say minimization means 0. So 0 minus 10,000 minus 10,000, 0 minus 20,000 minus 20,000. As we go on increasing the y value, the objective function minimization goes on decreasing. So there is no fixed point. So that's why it is called unbounded solution. For maximization, optimal solution is there. For minimization, as y is not bounded by taking higher values of y, the minimization goes on changing, minimization value, so keeps on changing. As you change the y value it will change, so there is no infinite value. So that's why it is called unbounded solution. Next, another case, z max equal to, we start with some new space, z max equal to 3x plus 2y subject to x less than or equal to 40, y less than or equal to 60, 3x plus 2y less than or equal to 180, and x comma y greater than or equal to 0. As a first step, convert that into intercept form. Less than or equal to 1 is one equation, y by 60 less than or equal to 1, x by 60 plus y by 90 less than or equal to 1. So after converting that into intercept form, we understand that x and y values ranges. So in minimum it should have it multiples of 20. If we take maybe 40, 60, 90, x value is only 40, 60, y value is 60, 90. Take multiples of 30. So if it is 60, definitely it has to come 90 here, somewhere around. So first one is x less than 40. X is less than 40 towards the origin. This is the first constraint. Next constraint, y less than 60. So y is less than 60. Second constraint. Next third constraint. X by 60, x has to be 60 and y is 90. So draw a line passing through these two, less than or equal to 0. So this is third constraint. The region which is common to all these three is the feasible region, and the corner points of this A, B, C, D, E, all these points are optimal values, not optimal, feasible solutions. For example, ZA is nothing but ZA max. We have know that 3x plus 2y, right? So substitute the values. ZA equal to 30 plus 2 into 0, 0. ZB is equal to 3 into how much, x is 0 plus y is b, y is 60 is equal to 2y 120. ZC 3 is how much, C point, ABC we need to should have. A is 0 comma 0, B is 0 comma 60, C is 20 comma 60. After if you simplify that, D is 40 comma 30, E is 40 comma 0. Substitute those values here. So B is done. C is 20 plus 2 60 180. ZD 340 plus 230 180. ZE 340 plus 20 120. So out of this, ZC is equal to ZD. So that means take any point between C and D on equation 3. The value is same, which is and is 180. So you are getting multiple solutions. For multiple x and y values, you are getting objective function same value. So this is a case of multiple solution. When you have multiple values which gives and which satisfies objective function, then it is called multiple solution case. Another problem: z max equal to 3x plus 4y subject to 2x plus y less than or equal to 4, x plus y greater than or equal to 10, 12 x comma y greater than or equal to 0. As a first step, convert them into intercepts. X by 2 plus y by 4 less than or equal to 1, x by 12 plus y by 6 greater than or equal to 1. So draw the graph x and y. Mark out the values x intercept 2, y intercept 4. So that is one line, sorry. It is 2 here. Okay, we'll just move it. 1, 2, 1, 1. Next, second equation x intercept 12, y intercept 6. So first equation is less than or equal to towards the origin, and second equation is greater than or equal to, so they are away from the origin. So there is no solution space which are which has positive value in the first quadrant. So yeah, they are meeting at somewhere in the negative quadrant, second quadrant. We need positive values, so we need x and y greater than has to be 0. So that in first quadrant they are not all intersecting. The region in the intersect region in the first quadrant is null, so that's why it is infeasible solution. So we have seen unbounded solution, infeasible solution, multiple solution, optimal solution. These are the cases of different cases in any linear programming problem. They may ask different types, but you better know each case how what is the scenario of each case, when we have to say it is multiple solution, when we have to say it's unbounded, and when we have to say it is infeasible. So these are the different categories. There is another last one, different method of different case. In the above problem, where we had z max equal to 3x plus 4y subject to subject to 2x plus y less than or equal to 4, x plus 2y greater than or equal to 12. Earlier it was x is greater than or equal to, now x is unrestricted in sign. Unrestricted means you can take negative values also, not only positive. Y is greater than or equal to 0. Now we have changed this to this way. Solution is, start the diagram. So in the same again, we know that x by 2 plus y by 4 less than or equal to 1, x by 12 plus y by 6 greater than or equal to 1. So 2, 12, 4, 6. This is x. This is x value and y minus x minus y. So we are allowing minus negative x values also. So there is somewhere intersect point this side. So this that's why the condition is changed unrestricted sign. Then the problem is having unbounded solution, because it's, if you substitute x equal to negative value and the problem is maximization, x value is minus 4 by 3, y value is 20 by 3. This is the intersect value. So if you substitute this value, the feasible region is this one. No, that is not the feasible, sorry. So feasible region has to be like this. So all the region whatever you'll get here, this is feasible region. It goes like this because one constraint is less than or equal to this side, another constraint is greater than or equal to, so upper side. So the minimum value of x, because it is maximization problem, so the maximum value, sorry, the maximum value is, if you substitute minus 4 by 3 and 20 by 3, that is the maximum value. We will get optimal solution, that is the best solution. It is point is a, for example. So solution is unbounded, but it is a optimal solution. Z a equal to 3 minus 4 by 3 plus 4 20 by 3 equal to minus 4 plus 80 by 3 is equal to nothing but 68 by 3. This is the optimal solution, optimal value for optimal solution. So in practical there won't be any negative values, so that's why. And if the problem, if they give unrestricted, then only we have to do this way.